Good afternoon, everybody. It is afternoon, it's 12. My name's Marc O'Regan. I am the CTO for Enterprise Architecture for the EMEA region. I'm also the regional CTO for UK and Ireland for Dell Technologies. Let me start by saying I'm really delighted to be here in this city. I love Helsinki. It's been a long time since I've been here, but I feel right at home. I live about 25 kilometers outside Dublin, and the weather is exactly like it is outside. So as CTO, really I get to spend my time in three core areas. One, obviously, in the office of the CTO, where we take in programs and projects. We look and examine new and emerging technologies. The second area that we spend most of our time is in engineering, where we take some of the inputs and some of the outputs from those projects, and we bring them into our own IT and into our own engineering arenas. And then the third area where I spend a lot of my time is actually with good people like yourselves in industry. So where we take some of that ideation, take some of the innovation, and we bleed that out into industry. So we spend a lot of time with new technologies and emerging technologies. And I just want to sort of, frame the conversation today in terms of IoT, how these new technologies and emerging technologies are having an impact at an engineering level, at an ethical level, at a cost level. They're all really, really relevant. There's a number of really interesting things that are going on here. There's a bottom layer and a top layer. The bottom layer is what I call the pillar trends, and the top layer is what I would call the emerging trends. At the top layer here, on the extreme right-hand side, we see a very interesting trend emerging here, and this is the incremental downturn of computing costs. So computing costs hitting near zero. Now, you could be forgiven for thinking that a guy like myself from Dell Technologies would take a very jaundiced view on that in terms of the impact it might be having on our organization. Quite the opposite. This is a direct impact of Dell Technologies and our relationship with standards, our relationship with democratizing IT, and our relationship with taking value to where it needs to be. And we examined three of those cores from a standards perspective. With some of our other good friends in this room, we were among the first to market to embrace the x86 standard, which is really at the core from an IT perspective of distributed architectures across data centers and beyond. The second area of interest is in the democratization of computing. As Dell Technologies, we have been ruthlessly driving down the cost of specifically distributed architecture for many, many decades. And the real reason for this is so that we can actually take our technology and democratize that across industries, across markets, and share this with people and organizations all over the planet to solve complex and organizational business problems. And then the third area is really an output of those two things put together, and that is by proxy, by driving down the cost of these architectures. What we're in fact doing is making it very, very cost effective to embrace newer and emerging tech. So that would be really a commercial, a commercial viewpoint. On the extreme left-hand side here, you will see this interesting trend where we have the explosion of technology and technological advancements. This is a real problem statement for a technologist or an engineer in this space, in the sense that we are now dealing with an ecosystem, I guess, whereby the architectures and the engineering and the technologies that we're dealing with on a day-to-day basis are accelerating by a factor of 10 every 5 years, which is a massive problem statement to try and deal with. Coupled with that, the types of problems that we're trying to solve with the architecture that we have within our hands today is changing. Pretty soon, we're going to be in a time when binary is just not going to be enough to be able to solve some of the problems that we're trying to solve with straightforward traditional compute. We're going to have to look at things like qubits within quantum computing and things of that nature to solve some of the problems that we're really interested in solving. And then all of this conspires together to bring us into this ecosystem, this concept, which we're calling Internet of Things. And as we all know, Internet of Things has been with us, for good or for bad, for many for many, many years and many, many decades. But all of these forces within industry and forces within our lives are coming together in order to bring us into this IoT space. And that IoT space is underpinned and can only work from end to end, from what we call from edge to core to cloud, when we look at these core pillars, as I call them, underneath here. So cloud, which emerged at the end of the last decade, really a new modern operating model, defined by software and adhering to the National Institute of Standards and Technologies in terms of a service delivery platform. Over on the extreme right-hand side, the services that we're now wanting to deliver across these discrete and distributed architectures are now very, very personalized, be that personalized for an industry, for an organization, or on a one-to-one level. And we need to be able to accelerate the emergence of these personalized services and get them to where they need to be extraordinarily quickly. Big data is another emerging tech at the beginning of this decade, which emerged around 2011 timeframe, which really now brings us into a world where we're not just interested in descriptive data or historical data, we're interested in prescriptive data and near real-time data and predictive data, something that can happen or hasn't happened yet and how we influence that. We're interested in dark data, structured data, semi-structured data, all types of data and as much of it as we can get our hands on. And then, of course, what we actually do with that data, because remember, data is only data until you unprise information from it. And this is where the conversation around artificial intelligence comes in. So right there, I'm just going to frame what I believe artificial intelligence to be. It's been with us for many, many decades. It was born really out of a number of conversations, a number of lectures, and a number of workshops in the University of Dortmund around 1956, if memory serves me correctly. But really, why is artificial intelligence exploding today? I believe, as a technologist, it's for three core reasons. One, better algorithms, better use of algorithms, and the blending of those algorithms in order to achieve outcomes. And it was spoke very well of by some of the speakers here today. The second is the development and acceleration of compute. We can now take ideation. So we've always had the front end of artificial intelligence, the ideation, the creative end of artificial intelligence. What has been lacking is technology coming up to meet that ideation, to be able to do something about it. And that has fundamentally changed now what we're doing with AI, with machine learning, deep learning, and things in the neural net space. And then the third thing is a cultural thing that has changed. It's our relationship with data, how we handle data, how we use data, how we apply mathematics and advanced mathematical models to data points, data sets, and other things in order to very, very, very quickly surface an event, surface a problem-solving equation, or make some sort of change. So as Marc said in his last talk, and quite rightly so, data is the new oil. And if data is the new oil, as a technologist, I believe that speed is the currency in which we trade today. This is just a very, very quick example of how we handle a traditional neural net model. We take data and as much of it as we possibly can. And the reason we get as much as we possibly can is that as we start to refine and tear that data down, after we get access to our data sets, we have a better chance of doing something reasonable or something different with it, something positive with it, achieving an outcome. So we go to our data sets, we extract data from our data sets and deliver them into our model, ingest them into our model in mini batches. We run this through the model and then we look for checks and errors using what we call gradient descent. So we start to iteratively churn the data through our model, refining it down into a model that we are happy with. So that's how we traditionally approach developing a model. What's really changed in our industry is that we have the analytics of the data analysis, it's what I would call causation, and then we would have the data science, the mathematics related to artificial intelligence, which is what I call correlation. So the causation side is really around how we analyze the data in order to get to a root cause of a problem or in order to surface a potential within an organization or a business. And that relationship is connected directly into the relationship of the mathematicians and data scientists who understand the algorithms in the neural net space. These algorithms here, which are delivering real and tangible value for us in life today and in life moving forward over the next number of years. And this relationship is critical, I believe, to the success not only of artificial intelligence, but to the success of IoT as we start to move through time. One of the speakers mentioned this earlier on. A C-suite understanding and endorsement and sponsorship of any modern analytics engagement is critical to its success, and I would absolutely agree with that. There's not one single analytics run that I've done or MVP that I've been involved with that has been successful that has not had C-suite buy-in and C-suite sponsorship. If we're trying to solve an equation or a problem, a yield problem, for example, in a factory, and we come across some sort of relationship in a robot or some sort of problem or a deficiency in the process that is related to a robot, we may have to actually programmably interface into that robot to make change. We think about what we're doing there, we're making a fundamental change to the entire manufacturing process. And if we don't have autonomy to be able to do that as technologists, we run the risk of ending up with a science project, which is what we want to avoid. These things are extremely difficult to do. When we try to distill this down and articulate it in situations like this, it's easier for us to explain this as, an entire continuum from edge to core to cloud. And building an ecosystem which deals with all of the elements that we see up here can be pretty tricky. We've got multiple devices, tens of thousands, if not hundreds of thousands of devices that we may want to go out, tag, and start to extract data from so we can make decisions that are near real time. I say near real time because, in my view, there's no real time. It's just gone. We've got all of the protocols associated with that, and I'll touch on that in a few moments' time. We've got the relationship between the edge and the core then, how we actually take the data across low and high band networks, how we actually, what data we take across that network, how it hits a core, and then the iteration that we do from a data analytics perspective at core and spinning that data out. And then how we actually tap into data sets in public clouds and then potentially even use public clouds for dashboards, things like Power BI within the Azure cognitive suite. For many, many different reasons. There could be a technological reason why we may need to go to public cloud for scale. There could be a compliance reason why we can't actually put data in cloud, but we can still use tools like Power BI, which are quite powerful tools for dashboarding, etc. Nevertheless, this is extremely difficult stuff to do. We have data, lots of data. We mentioned earlier on descriptive data, prescriptive data, structured data, semi-structured data, etc., etc., etc. We have analytics, lots of analytic platforms, lots of analytical techniques that we can bring to bear in order to help us make this happen. We have a security problem, which is top of mind of pretty much any CEO that we speak to, any CEO that I'm speaking to. Security is absolutely number one on top of the list. As we start to explore and expose different capabilities at the edge, we're actually creating a new potential attack platform, and we need to be cognizant of that as we start to architect and move our capabilities out to the edge. And finally, we have the aligned stakeholders. So there's buy-in from the C-suite, yes, but there's also an approach whereby if we're having a conversation with an organization, we will bring in different line leaders to give different points of view of what the world looks like through my lens. Because 9 times out of 10, when we do that, we can start to surface and percolate different use cases which are relevant to that individual line leader in their organization that plug directly into the core KPIs of the business itself. It starts to get really, really difficult then when you look at the edge, core, and cloud and all of the different elements that you need to tackle, that we have to go after and look at from a consideration perspective when we're considering IoT. At the edge, we have all of the devices, everything from PLCs to pumps to actuators, SCADA, mobile phones, whatever that device point of interest is. We have all of the protocols associated with that, BACnet, Modbus, CAN bus, Zigbee, Wi-Fi, a number of different protocols, which we'll get to in a moment's time. And as we start to take this in, there are technological considerations, ethical considerations, governance, compliance, control considerations, bandwidth, and speed considerations and accuracy considerations that we need to take in as we start to deploy architecture out into the perimeters of the edge. One risk that many CEOs run is that they get infected when looking at all of this by what I call the cloud-first virus. So way back in 2007, 8, and 9, I was lucky enough to get onboarded onto an engineering build team for a project called Red Dog, which later became Azure, and saw firsthand how on one side of the table we had a lot of CEO personalities who are looking at the promise of what public cloud can bring to the table, and it does. It did and still does. But on the other side, we would have had the more conservative CEO who sat back and said, I see what this is, I see the potential that we can get here, I can see the scale, the elasticity, the extensibility of what this kind of new operating model can bring to our business. But there's risk involved, and I just want to sit a little bit back. Those CEOs, 9 out of 10 of them today would embrace public cloud in some way, shape, or form, and do so rightly. It's around understanding what to put in public cloud, how that will scale, how that will behave, the cost structures involved, and what is going to work for your organization. The risk of putting everything into a public cloud, apart from the traditional things that you'll hear around security, et cetera, is really a potential that you can lock yourself out of exploring what is on the perimeter, what you can tap into, an API into, and extract information from an IoT perspective, in my view. The other risk that you run is that we can port any old device out onto an edge and lob a data model onto it. Now, this is a real engineering question at the moment. So I got really excited when Raspberry Pi emerged. As a matter of fact, I was speaking with one of our colleagues a little earlier on. I got 5 of them at home myself in a little tiny HPC cluster in my room where I do a little bit of coding. These are really exciting technologies, don't get me wrong. The point is that there needs to be careful consideration made when adopting the kinds of technologies that we're after, because there's problems from an engineering perspective that we're out to solve. One of the problems is a computational or a compute architecture problem. So we have a CPU up here at the very top where the red line is. My background is in high-performance computing, and one of the things in HPC that we were really interested in doing was getting the compute as close to the data as we possibly can, for many, many different obvious reasons. And this is going way back. It underpins the principle of distributed architecture. So from an engineering perspective, when we look at silicon, we're really interested in getting that silicon as close to the data source or the data point as we possibly can. There's a problem in that, because as we start to build models within AI, and we start to develop extremely intelligent, capable models and inject them to the edge, we need the compute horsepower at the edge to be able to actually run and turn those models. Now, there's some interesting stuff being done in industry where we're seeing a lot of yield come out of in-memory type of models. And this really is going to be, for me, the source of the future. You can see actually in the data center where over the last 8 to 10 years, a lot of in-memory technologies is making its way into solving problems at a data center level. We're taking that a step further in industry, and we're actually creating architectures which are in-memory-based architectures which can get out to these extremities and have a real impact and give us the capability from a horsepower perspective to tackle these problems, but also to hold these models and distribute these models across the arenas that we're interested in. The other problem that we have is how we handle all the movement of the data that we just mentioned a few moments ago, but also how we look at the protocols associated with the different devices. I mentioned it earlier on, BACnet, COM bus, Modbus, Zigbee, Wi-Fi, There's a lot of different protocols, tens of thousands of protocols out there. How do we normalize that data in near real time while still providing a device that's sitting out at the edge that we can drop a model onto? So again, and another theme that's being mentioned quite broadly here and something that we're extremely passionate about, collaboration is key in how we actually do this. So for example, we would be collaborating in industry with the Linux Foundation, where we've developed what we would call a standard that we worked on within projects about 3.5 years ago. We jettisoned this out into the open communities. It's called EdgeX Foundry. And that does exactly that. It normalizes all of the protocols that are coming in off edge devices. We deploy this out to the edge using SDKs and microservices that are sitting in devices at the edge layer. So we get the compute problem solved, where we have much yield and little or no power constraints. We get the horsepower problem solved, where we're actually able to deploy devices out to the edge to make in near real time decisions using artificial intelligence, machine learning and deep learning. This is when we get closer to actually building out what I believe to be the core framework of an IoT infrastructure, or an IoT ecosystem. So when we look a little closer at that, we have the edge tier, we have the platform tier, and we have the enterprise tier. At the edge tier, we have our sensors. We have data collection. We have potentially data analytics of some sort going on out at the edge. And then we have the movement of data, or data transit, from the edge to the core, where we will have the analytics. So the analytics could be, I don't know, a Hadoop instance from the Apache framework. It could be SAS, it could be SAP, whatever that looks like. We'll also do our inference there. So we'll conduct our data science there. So the data that we're taking in from the edge, we're bleeding into a data lake, or a data engine, as I prefer to call it, refining a model and pushing that back out to the edge in some cases. And we're also tapping into the enterprise and blending some of that near real-time data with our CRMs and different enterprise application stacks. We need to manage the data. So as we build these models close to the edge, we need to be able to actually surface dashboards that are going to give us accurate statistics based on the metrics and telemetry that we're pulling from these environments, but can do so in a way that is meaningful to the person or organization that's viewing these statistics from a platform. We also need to secure these environments. And we can do so at many, many different levels, actually using artificial intelligence in some ways to develop security models that sit on top of the machine learning and deep learning models that you've injected into the edge and that are here at the core. And as you start to embrace public cloud, they're protecting that as well. The whole continuum from edge to core to cloud coming together means that we're doing things like using streaming data, so taking our batch data and taking data and metadata from different points and streaming that across low and high band networks, giving us the opportunity to sense what's out there, make a decision to act against something happening, or potentially prizing open a new opportunity based on the data and information that we've been given. So we can sense what's going on, we can analyze what's going on, and then we can act on that. It's what we call the innovation circle. So by implementing and architecting accordingly within the data center, within the edge arena, and within cloud, we're actually building what we call a system of systems. The elements of what we're talking about are pretty new or advancing, but we've seen the movements happen pretty systematically, if you look at it, throughout every decade, or every bi-decade, as it seems to be. If we go way back to the early 60s, we would have had the emergence of the mainframe, which centralized things. About 15 or 20 years later, we had a distributed model with client-server, In the early 2000s, we would have had this move towards a cloud or distributed architecture based on cloud, and then distribution or a distributed model is starting to come in towards the end of this decade and into the next decade. So there seems to be this systematic step change every 2 decades. The real area of interest for us is what we can actually do with edge computing. If we take machine learning, residual models, recurrent models, things in the deep learning space, getting the intelligence and getting the horsepower right out to the edge becomes extremely important for us. It allows us to actually build the types of architecture from an ML and DL perspective and execute out on the edge. Some examples of where we're doing this, there's various different examples. If we look at what we're doing with GE, so we're taking data from an in-flight aircraft and we're taking telemetric and metrologic data that's streaming off the engines. We're interested in examining the metrics in terms of the engine performance. We're interested in looking at the altitude that the aircraft is actually flying at, and if we can get that up to a higher altitude, we can actually save on fuel. We're making changes in near real time to the craft. We're looking at destination data, so using GPS data and other data, so we can actually shorten the flight path of the aircraft. We're doing all of this with partners as well. And if you take that concept, one program that I'm working on right now at the moment with first responders is taking telemetric and metrologic data off machines within the inside of the ambulance cab. And we're also taking this data off wearables. And this is specific to a program that's interested in patients who have suffered cardiac arrest. So what we're actually able to do is take near real-time data of an ambulance in transit and stream that data to what we call micro data centers. So these micro data centers are sitting at or near cell towers, dotted around the country. So as the ambulance starts to move through the country with the patient, it's taking all of the vital statistics from the patient, from the wearables, and also taking all of the telemetry that the diagnostic systems and the machinery within the inside of the cab are feeding to us, and we're able to make a call to the hospital to let clinicians and surgeons know that this patient is going to arrive to you in such a state, prepare for surgery or prepare for intervention of some sort. We're able to take this type of capability, to terminals for, credit cards. So MasterCard would be a very, very good example of where we've done this before at a global level. So this is really using artificial intelligence to build models in behind the MasterCard network, which does checks and balances. So I would have traveled to Helsinki from Dublin today. MasterCard will know that part of my profile is that I travel a lot. It will know who I am. It will do checks and balances in the background, and prevent me having to wait at the terminal. That's MasterCard's KPI. If we don't think about the MasterCard, then there won't be a problem. It's a good experience. The other thing is that we're actually building security, custom-built security models around the network as well as part of it. So there's a number of different areas where and capabilities that we're interested in. This is the part where I hope you don't jump up and go away. You look at this. This is just a real example of where we're doing this ourselves. So here you see a number of different steps. There's 8 or 10 of them, whereby we're spinning up an entire environment for our data center, hardware delivery. And what we've actually done is taken those 8 or 10 steps and pull them into an AI automation script. So in a very autonomous or autonomic way, we can request infrastructure from our data centers. We can evaluate that infrastructure, map it to the dependencies of the applications, spin it up, orchestrate the spin up of that data center, analyze it, and then decompose it and give it back to its engine. And then the very last example that I'll give you is what we're doing in the federated analytics space. So this is really taking what we call a novel computational pattern and taking what we've learned from doing a lot of work with the likes of TGen, a non-for-profit organization that we did genome decoding programs with over the last 10 years, and applying that to a federated analytics model. So what we've learned with TGen is that we can take advanced AI and federate that across multiple geolocations. And it kind of works like this. You will have distributed research zones on the perimeter here and a core analytics zone. And what we're doing is we're distributing the analytics to the research zones and then pulling the metadata associated with the analytics into the core. So if we look at this, there's an analytics fabric up at the top where a researcher inputs a query into a query engine. And then we have a federated data zone fabric where we're actually talking to different sites. A site maybe in Helsinki, a site in Dublin, a site in Boston, whatever that is. The researcher quite simply puts in the query into the research engine. It's then distributed across what we call virtual nodes. So those virtual nodes are going to do the iteration, are going to do the initial computations. Once that's done, we're pushing this out to the individual sites in their different geolocations, and we're actually doing the analytics there with compute architecture that's already resident on site. Once we actually surface a return from the analytics that we're doing on site, we take metadata, not data, but metadata, and surface that metadata back up into the virtual computing cluster. That's solving a number of different problems. One, data residency and data privacy in the sense that the data never leaves the research center. Two, the network between the data center at the distributed data zone is protected as it makes its way to the virtual fabric here, and plus the network can be thinner, so we're saving on latency issues here. So that's just one way of how we're actually handling a distributed and federated model. There's many different configurations and use cases that we can feed into this. So just to finish up, from a collaboration perspective, it's absolutely key to any IoT engagement that we're involved with. We have a wide ecosystem. We depend on our indigenous and global partners for our success. There's many programs worldwide that we're leading. There's many programs worldwide that we're involved with that are being led by different partners. But it's key to our success. Within IoT, just to summarize, we see this as a continuum that needs the input and continued SME-level engagement from ourselves, from our partners, in order to solve the types of complex business problems or opportunities as well that we're trying to surface. Thank you for your time. Enjoy the rest of the event, and I'll talk to you later. Thank you.